All right, greetings, folks. This is Rob for Central Apologetics. I'm here with Dr. Hugh Ross, uh, a gentleman who I consider not only a brother in Christ, but I would also consider a spiritual father figure as far as the faith is concerned. Definitely a hero of the faith of mine. And it's a pleasure to bring you on for the third time on Sentinel. And your ministry has been an absolute blessing in my life. It's definitely been a blessing. Like, I read comments when I put a lot of your material, and when I highlight a lot of your key points in your material on my channel. I even read comments by people that are just, encouraged by the insights that you've provided, not only as a scientist but also as a theologian. And yeah, thank you, Hugh. Thanks for coming on again.
Oh, you're very welcome. It's my pleasure.
Well, you're about to release a new book.
Yes,
And
going to the core.
yeah, here is the cover page of this particular book. And I would like to, for everyone in the audience, I'd like to play a short trailer that are to be developed, just to give a flavor, and then from there we can jump maybe into a little bit slightly more specifics. You don't have to share too much, or say again like why you wrote the book, and then from there we'll jump into some, well, as the title of this interview is called, a cosmic snapshot. So basically, I want to present to everyone Hugh's work and the RTB model all the way back from, say, the 70s down to this year. And I think everyone will be quite not only surprised, but I think everyone needs to be informed and sort of like brought up to speed with the positive developments that's been taking place. So, all right, here is the trailer.
Is the universe on the brink of destruction? Or is it the perfect home for humanity? From a strictly astronomical perspective on time, doomsday for humanity and all life appears to be just around the corner. But I'd like to offer a different point of view to consider. While one person sees a razor-sharp blade as a deadly weapon, the other sees it as a life-saving scalpel. My hope is that the new astronomical research presented in my book Designed to the Core will inspire you to arrive at this conclusion, that the motive of the one who wields the blade makes all the difference. Our universe has been designed with intention and purpose, that everything has been set in place to make human life and thriving possible at this very specific time. Early access to Design to the Core is available now. To receive this book before its official launch in September, visit reasons.org/donate and make a contribution of any amount to our ministry.
Sweet. So Hugh, how many years have you been, or how long has it been that you've been writing that particular book?
Well,
And yeah.
yeah, the books that I write on scientific topics with the idea of presenting additional scientific evidence for God, the typical complete writing time is about 5 years. It doesn't take me that long to write the book, but it does take many years to do all the background research, because I always exhaustively read the scientific literature on the topic before I begin writing the book. And same thing with
Hmm.
the theology books I bring out. I want to first do the background research before I put pen to paper.
Hmm. Now, I have a clip, a 2 minute clip.
So that you
Whoops, sorry. So I have this 2 minute clip. This is from 2008. This is on the right is Victor Stinger. On the left is Hugh Ross. This is at Caltech, I- right? And
That's
the
Caltech.
debate, right? And so this is probably the best debate as far as like legitimate, like in this case Hugh Ross, right? A legitimate scientist in the field of astrophysics, going head to head with, say, someone in the same sort of field, Victor Stenger, and again, a robust scientific creation model being put to the test in front of an audience of what was it, 300 atheists or something in that audience, and
There were 700 atheists
oh,
from around
700,
the world.
yeah.
There were 5 physicists who were atheists that spoke before the debate, and they were all promoting the idea that astrophysics shows that there is no God. And so the debate was at the end. The Skeptic Society sponsored the debate, and this was one of their meetings of the International Skeptic Society. So yeah, we literally had skeptics and atheists from around the world.
Mm-hmm. Now, near the end of the debate, well, as the debate transpired, I noticed Victor started to show a lot of respect to you. Like, as near the end of the debate, he started to really like give credit to you in your approach on this. So then this inspired one of the audience members to ask this very interesting question. The clip is about 2 minutes, and then your response here, I think, is quite relevant for this interview as well.
Dr. Ross, you said that you had a testable and falsifiable set of evidence for a creator of the universe. Yet it seemed like all you did was provide a huge number of how unlikely it was that we would have conditions that were conducive to human life. And that by virtue of the fact that we are here against such odds, that your claim was not falsified. It was in fact reinforced. That just seems like a very weak sort of argument to me, that it's really unlikely that we're here. Was there anything that I missed in that? Was there more depth to this verifiable and falsifiable method that you had?
Sure. Keep in mind, I was limited to just 25 minutes. What we're doing at Reasons to Believe is developing a set of tests. We actually classify them into 3 categories. Things that would actually falsify our model to such a degree the model would be done. For example, if we were to prove scientifically there's no beginning to the universe, or there's nothing special about humanity with respect to, say, clams and oysters and bacteria, that would be catastrophic to the Christian model that we're presenting. There are other things that would be simply corrosive to our model. It wouldn't destroy our model, but would require major adjustments to our model. And then there are discoveries that would simply refine our model. And what we're trying to do at Reasons to Believe is to develop these 3 different kinds of discoveries that would be, catastrophic, corrosive, or refining, not just for our model, but different models within the Christian realm, and then models outside the Christian realm, covering the whole creation evolution spectrum. That's really the way to put these different things to the test. And I would say it's incumbent upon every model developer to come up with a list of things that would confirm, and that's kind of what I focused on today, confirmations. I didn't have time to get into things that would not confirm the model, things that would be corrosive, catastrophic, or simply fine-tuning adjustments to the model. And if you want to see how things have developed, I've been working on this since 1973. I've come up with 5 editions, for example, of Genesis 1 as scientific interpretation, and you can actually see the evolution of the interpretation of our message concerning Genesis 1 over the course of those 35 years. But what you see is that the refinements, we're not seeing anything happening within science that is corrosive or destructive, which means maybe our interpretation really has validity.
That was a fantastic answer. And mind you, folks, that was in 2008. Now we are in 2022, and a lot has transpired since then. In fact, I remember in that debate, you even, to Sean Carroll, you said, hey, if there's gravity waves, if there's a discovery of gravity waves within 5 to 10 years, that can lend validity more so to the Big Bang creation model you're proposing. And I know they're still sort of looking for that because, the 2013, 2014 findings are still a bit muddy or something. But I remember Sean Carroll himself, within the 5 to 10 year bracket, actually telling his audience, like, look, I need to update my data points. But then because I'm a careful listener of your work, I made the connection to your prediction to Sean Carroll back in 2008. And so that's why I actually made it's on Sentinel. I made a video titled Lawrence Krauss defends the Genesis creation account. It's a tongue-in-cheek comment because in 2013 he was at the some Nobel Prize conference for the universe or something, and he was giving his key lecture. He had a number of cosmologists on the panel, one of which was a like a like he was a bishop but also an astronomer. I forget his name, but anyway, the point is, it's just interesting that you're staying cutting edge with the scientific literature, and you're not afraid to give predictions and share predictions, right? And you're also having the biblical text as a I suppose like a base layer, like a grounding to sort of to encourage you to further make that prediction. And again, the amazing thing is it's always coming out on top. So yeah,
Yeah, there's a principle you see in Psalms and Proverbs that the more we learn about nature, the more evidence we'll uncover for the supernatural handiwork of the Creator to make possible the redemption of human beings. And that's kind of a new development in our testable, falsifiable, predictive creation model. We look at the Bible, and it tells us that God begins his works of redemption before he creates anything at all, which has the implication, or at least the suggestion, that everything that God creates is going to be for the purpose of making possible the redemption of billions of human beings on a single planet from the propensity to sin and to commit evil. And so I've been challenging my scientific peers who are not believers and saying, look, I know you're not a Christian, but if you'll simply do your scientific research from a biblical redemptive perspective, it will make you more successful in making scientific discoveries. Put it to the test and see what happens. And that's kind of the focal point of my latest book, Designed to the Core, is saying, if indeed everything that God creates is to make possible the redemption of billions of human beings, we should be able to examine the universe on its largest size scales and at every size scale, from the very largest size scales all the way down to the smallest. So the book begins by looking at the design of the universe to make possible humans existing and the redemption of humans from their sin and evil. And then we look at the cosmic web. We look at the super galaxy clusters, the galaxy cluster that we're in, the local group of galaxies, our galaxy, the local bubble, the local fluff, down to our star, the planets in our solar system, even the 5 asteroid belts we discover are fine-tuned design to make possible the redemption of billions of human beings. And we call it Design to the Core because the book kind of ends up by looking at the core, the interior features of the sun, the moon, and the earth, all the different interior layers of the moon and the earth, and say in every case, it's designed to make possible the existence of billions of human beings on planet Earth so that they can develop the technology whereby billions of them can be redeemed from their sin and evil in a relatively short period of time. And we look at Design to the Core as a launch pad because we want to do this in all the different disciplines of science, not just astrophysics. And so my colleague, Fazal Rana, he's planning to do a book where he does that at a biochemical level.
Mm. And oh yeah, that would have major implications with the other texts you and Fuzz have written. So, for example, Origin of Life. That in itself is an entire study, which is yeah, like you wrote that in 2004, but you also
Right.
have on your website a companion website like sticking up to date with the latest on Origin of Life research. And
Right.
then Improbable Planet would be, I think, again, like a telescoping of, say, just focusing on Earth. You know, like you're giving, I suppose like, Design to the Core, as you're explaining, it sounds like, you know, like, like from a sky view perspective, down, zooming and zooming and zooming into now
Right.
the
Right.
Earth. and then you have your other texts that I recommend everyone to read. You can read maybe like side by side. Like Improbable Planet would be specifically about Earth. Origin of Life would be, say, origin of life with respect to what's happening on Earth. Um, yeah, this I just want the audience to see this is how robust the RTV model is. It's not just it's not
Yeah,
just
we've
books
got
here and
over
there for the
30
sake of
books.
writing, and
There
yeah.
are now over 30 books, basically amplifying our testable predictive creation model. I mean, Fuzz and I co-authored a book on human origins, and we're realizing, what's a core feature of the Christian faith is that we humans are exceptional. We're unique amongst all life on planet Earth. We are spiritual beings. We're not just physical beings. So Fuzz and I are actually going to be developing a book that's going to focus on human exceptionalism. And I've actually just been, they basically told me that they've agreed, there's a peer-reviewed scientific journal in Asia that has invited me to be an editor of a special issue on human exceptionalism. So we're going to be inviting
Mm,
scholars from our scholar community to submit articles. And
mm,
so that's the other thing we're doing is people saying, hey, if you got a testable creation model, why can't you get it published in the peer-reviewed scientific literature? Well, the
mm,
truth is we've had half a dozen articles published, but now that I'm stepping back from being the president of Reasons to Believe, I'm actually launching a project to have a lot more than just a half dozen articles in the peer-reviewed scientific literature, where we actually play the God card, where we say this isn't just science for science sake. It has deep, significant philosophical implications. Because a lot
mm,
of the scientific papers I cite for design to the core, they'll end by saying this is a habitability requirement or a habitability criteria, but they stop there. They don't take the philosophical leap and say, what does this really mean? So that's what we're
mm,
trying to do and actually get it in the peer-reviewed scientific literature. And I think you're in a good location, Robert, because, you know, I remember David Block and I submitting these papers back in the 1990s to European journals and American journals. And they said, hey, you two are Christians and you're promoting the Christian faith. And we're not going to
mm,
publish this, no matter how good the research is. What we're
mm,
discovering is that journals in Asia in particular, they're okay. They're saying this is what publication should be all about. We shouldn't be trying to put shackles on you. So now I don't know how far we're going to be able to go with that, but we're going to give it a go.
mm. It also comes full circle to the spirit of someone like Thomas Torrance, who I've seen you also cite in your work, the theologian who himself was a commentator on Einstein's works. He was a scientist in his own right, and like when he wrote Space, Time, and Incarnation and the Grammar of Theology, like Reformation Europe, Christian theology is the reason why the scientific method even is what it is. And then now with all this fantastic, like, look how far we've come as a species, I suppose. Like for example, like the background image I'm using here is the latest image from the James Webb Telescope, and
Right, right.
your work is highlighting, like, okay, let's put God aside for a moment. At least, even though you're a Christian, you're still trying to encourage people, regardless if they're Christian or atheist. Look how beautiful reality actually is. And then that is the bridge, because then, as you're pointing out from the biblical theological point of view, if God already has a two creation model in mind, like, if the first creation is already the way it is, it's then, like, obviously you should ask the question why, and then there's the bridge that will lead to the second. So,
Well, you mentioned
basically
Thomas
a Romans
Torrance.
120 moment.
Right.
Sorry?
You
Yeah.
mentioned Thomas Torrance. He invited me up to University of California, Berkeley, where he had a grant to assemble uh, a dialogue for a weekend between 15 physicists and 15 theologians. And I was the only one there that was actually in both camps. And so
Okay.
what he shared
Yeah.
with me is that he had developed a talk where he simply communicates to scientists in about 22 minutes how beautiful the nature, the world of realm of nature really is. He says there's beauty there, and it's everywhere, and the mathematics and the astronomy inside the cell, in the human body, it's ubiquitous. And he says, I've used that as a tool to bring research scientists to Christ. And he was telling me about some of the, atheist scientists I was aware of. He says, yes, I was able to communicate and bring them to faith in Christ. And then he joked with me and said, I've seen you in operation this weekend. You seem to be committed to evangelize theologians and bring them to faith in Christ. And he said, you've got a much more difficult mission than I have. I'm a theologian trying to bring scientists to Christ. You're a scientist trying to bring theologians to Christ.
Yeah. All right. Now, can you briefly go through for those who are not fully aware, because I think this will, once we lay this groundwork, then the rest will make sense. Basically, the basics of Big Bang cosmology. So I have here. Let's start with Kobe's first measurement. What was going on with Kobe's first measurement?
Well, you show the temperature profile, the cosmic background radiation, and what Kobe was trying to do was measure the temperature to better than 1 part in 10,000, because we see galaxies and galaxy clusters in the universe. And so a prediction of Big Bang cosmology is that if we were able to measure the temperature of the cosmic background radiation to high precision, we should see over the sky temperatures that are very slightly warmer than other regions of the sky, and that the hot spots we see would coincide with the future galaxies and galaxy clusters and super galaxy clusters. And until Kobe was launched, we didn't have any measurement of the cosmic background radiation with sufficient precision to see those predicted differences. And Big Bang cosmology actually predicted that as we look at the sky, we're going to see temperature differentiations of about 1 part in 100,000. So that was an actual number. If the Big Bang model is correct, these are the temperature differentiations we should see. And I remember talking to my fellow astronomers back at that time, and they said, what if we don't see those temperature differences? That would be catastrophic to the Big Bang creation model. And maybe there isn't a beginning to the universe. And maybe we've made some mistake with these space-time theorems that seem to prove that there's a beginning to space and time. And I remember my fellow astronomers kind of nervous because they saw all this observational evidence for the Big Bang, but they said, if Kobe doesn't come through, we're done. And then Kobe did come through, and it barely detected differences. I mean, you just see some hot spots and cold spots. It wasn't as sensitive as the Planck satellite, which shows it in detail. So much detail, you can actually look at the different hot spots and actually see that they coincide with super galaxy clusters and galaxy clusters, and that the cold spots coincide with voids between the clusters. So now we've got a detailed confirmation thanks to Planck. But it was Kobe that basically had all the astronomers kind of wiping their brow and saying, the Big Bang passed a really crucial test.
And this was in 1989, right? The first measurements. And so here's the crazy thing. I was born in 88, so I was 1 year old when these results were released. And then there was a refinement in, I think, 91. So this is now the next slide where there's a much more refinement curve. And then, so this is a highlight from your text where you showcase snapshots of, from 14 billion years, 9 billion years, 5 billion years, 2 billion years.
Right.
Now, now we're definitely jumping forward now. This is obviously in the 2000s where you're talking about dark energy and dark matter, because I'm presuming the whole dark energy, dark matter stuff wasn't around with Kobe, or was it maybe hinted at, but only now are these measurements due to Planck, are they measured now, and why?
Well, people were talking about dark matter and dark energy and ordinary matter as far back as the 1970s. But I remember in the 1970s, astronomers were saying, we're never going to have an instrument that can actually detect the possible existence of dark energy or even dark matter. But we think that this is really what Big Bang cosmology predicts. And, we were pessimistic in the 70s, but once we got into the 21st century, said, hey, the taxpayer is actually willing to pony up more than a mere $1 million. We can actually get the instruments that can actually determine whether or not the universe indeed has these predicted proportions of dark matter, dark energy, and ordinary matter.
Mm. And why were we, so before we made these measurements that you're saying here, why were we making those predictions? Is it because of, again, the math involved with the, like it's a mathematical prediction if we're talking about an expanding, like a cold dark matter model, right? The lambda
Well,
CDM model,
yeah,
right?
what was happening
Yeah.
in the 80s and the 90s, we're getting more accurate measurements of the age of the universe and hints of its spatial geometry. And it was really looking like the spatial geometry was going to be flat. Not flat in 2 dimensions. The universe actually has 9 dimensions of space. So a 10-dimensional flat system, including time. But for that to work, you would have to have a certain percentage of matter that doesn't interact strongly with light and much more dark energy. And so it was around 1999. Well, a Nobel Prize was given for the discovery of dark energy by looking at supernova measurements. And they wound up giving it jointly to the team that announced the discovery in 98 and 99. But as I read the research papers, the 98 discovery was quite tentative. The 99 discovery really nailed it. They said, yes, we really do see the universe expanding more slowly in the early history than it does in the late history. And the only way that would happen is if you got a lot of dark energy.
And in your book, Why the Universe is the Way It Is, you do like a simple addition where you add it all up, right? And it adds up to 99.73% dark stuff, right?
Right.
And only 0.27 is what, visible, ordinary, something
Yeah,
like
the
that.
stars, galaxies, nebula, dust clouds, planets, all that adds up to 0.27%. The rest of it's dark stuff.
Yeah.
And if that wasn't the case, we wouldn't be having this interview. There'd be no light anywhere in the universe.
Is that the reason why Victor Stinger in the 2008 debate, remember that right at the end when he had his, like when everyone's given like a 2-second final closing, he goes, "We're all frozen nothing." Is that sort of similar to that? Like he's tongue in cheek with,
Well,
because
he
of the
was
way
brilliant because I talked to him afterwards and said, Victor, what I appreciate is that you were an honest atheist. If there is no God, then all of us are no better off than a cold rock. We're all cold nothing. And he said, yeah, I really get upset at atheists that try to think we've got some purpose or destiny or value. Says none of that's possible if there is no personal being beyond the universe. He says, I don't think there is such a personal being, which means I'm no better off than a piece of dust or a bit of dirt, a bit of cow dung. It's all the same. We're all cold nothing.
But you see, the point then is when you highlight 0.27%, or both, either way, like the 99.73 or the 0.27, the point is that in itself is a fine-tuning parameter, again,
Right.
for us to have this discussion.
Right,
Yeah.
it is. Yeah.
Yeah.
I mean, everything you've got here in this table must be fine-tuned for light to exist anywhere in the universe.
So then this becomes so this one was the cosmic density components. This one is basically in your fourth edition. You give an updated, the latest precision measurements of the cosmic expansion rate, and sure enough, there's a lot more going on. Here's your cosmic expansion rate, kilometers per second per megaparsec, and now this mean value here, 68.64 plus or minus 1.83. What's the significance of this
Well, what I
value
was
here?
doing here is saying, yes, we have these different methods for measuring the cosmic expansion rate, which also gives us the age of the universe. And what was unique when I came up with that fourth edition is the first time we had this degree of consistency amongst the measurements. You look at the numbers, and they're all hovering around 68, 69, 70. Whereas I can remember even 6 years ago that you had a much greater range. And so we're narrowing in. And, that's one of the motivations for the James Webb Space Telescope is actually to measure the cosmic expansion rate, not only in the nearby universe, but the distant universe. And one of its goals is to actually demonstrate that when you've got roughly 70% of the universe dark energy and another 26% that's made up of dark matter, you're going to have the cosmic expansion rate constant to about 0.75% throughout the entire history of the universe. But because of dark energy and that dark matter, we're going to see a slightly slower expansion rate, say when we look at galaxies 12 billion light years away, than we do when we look at galaxies that are only 1 billion light years away. The James Webb Space Telescope has the potential to make those measurements with high enough precision that we're actually not only going to measure the average cosmic expansion rate, which is what you see here, but actually measure the way it has changed over cosmic history with sufficient accuracy. We're going to come up with a much more detailed cosmic creation model than we have right now.
Amazing. So then, I know you highlighted this when you came to Perth because I remember this particular dot over here. I remember because you came to Perth in 2014 and you made it. You specifically said just a couple of weeks ago I had to put this added data point because of a very recent publication. But yeah, this is the CMB temperature. That's from a would you say near infinite temperature, and it's coming down in a predictable way. These are obviously some error bars, but there's the mean curve here fits quite nicely, and sure enough, the analogy that you use is like the car engine, I think, and for the lay audience, maybe if you can summarize what's going on here.
I mean, one of the things you see in the Bible is that the laws that govern the heavens and the earth are constant. They don't change. And it's something we astronomers can affirm by looking at distant galaxies. We can look at the spectra, and that will tell us what the laws of physics were when that light left that galaxy. And by that means, we can observationally demonstrate that the laws of physics are not changing by more than 1 part in 10 quadrillion per year over the entire age of the universe. But one of the laws that governs the universe is thermodynamics. And thermodynamics applies to everything. I mean, our bodies are wearing out as we get older. Everything is decaying. That's a principle you see in the book of Ecclesiastes and in Romans. Everything in the universe is undergoing decay. And the principle you see in your car engine is that when a system expands, it gets colder. And so your car engine, if you got a diesel engine, for example, you don't need a spark plug because there the piston compresses to such a degree it raises the temperature sufficiently to ignite the gasoline. But when that happens, the piston expands. And when that happens, the temperature goes down and the gasoline stops burning. That applies to everything in the universe. And so with the expanding universe, it's going to get colder and colder as it gets older and older. And what this graph is measuring is the cooling of the temperature left over from the cosmic creation event. So when the universe was created, it was nearly infinitesimally small, and therefore its temperature was nearly infinitely hot. But as it expanded, that temperature declined. And it's going to decline exponentially, as you see in this curve, and in a highly predictable way. If you know the age of the universe, you can, based on Big Bang cosmology, predict how the universe would cool. So I actually refer to this as a biblically predicted cooling curve for the universe. And one of the ways of establishing the biblically predicted Big Bang creation model. I always make the point, if you read the Old Testament, at least 3, if not 4, of the fundamental features of Big Bang cosmology are explicitly and repeatedly stated. So I say we always give credit to Lemaitre and Einstein for Big Bang cosmology, but the real credit goes back to Moses and Job and Jeremiah, King David, Isaiah. They were the first to write about Big Bang cosmology. And so we can quite accurately measure the temperature of the radiation left over from the cosmic creation event in the nearby universe. That's what you see there at the end of the curve. I mean, why I was so excited in 2014 when I spoke in Perth is that little measurement you see in the middle. The error bar is smaller than the thickness of the line. And it was exactly right on the line. However, where we're going to need the James Webb Space Telescope is to reduce the error bars in the early part of the universe. I mean, what would be a big success for Big Bang cosmology is to actually get accurate temperature measurements of the radiation left over from the cosmic creation event, not just for the past 7 billion years, but say for the past 13 billion years. That's one of the motivations of building and launching the James Webb Space Telescope. Now, I've been looking at this for several years, and you notice how big those error bars are, but notice the center, the actual measurement, is really quite close to the line, which means that we've probably overestimated the errors. And those error bars you see are not just the random errors, the system, the random errors, the statistical errors in the measurement. They also include the systematic errors, taking into account that maybe we don't fully understand the physics of the spectral lines we're looking at, and maybe there's interfering factors. But notice in each case, the error bars are way bigger than how close the actual center is to the line. And, I've written an article in my weekly blog, Today's New Reason to Believe, where I talk about how astronomers, for the first time, went back not just 9 billion years, 10 billion years, they went back 12 billion years. And so we got 2 more measurements we can put on this curve. And what's exciting is both measurements are right on what we'd expect from the biblically predicted curve. But James Webb is going to be able to give us measurements as precise as what you see in that one about 7 billion years ago. They're going to be able to take that all the way back to about 1.5 billion years ago. So we should see some dramatically better confirmations of the biblically predicted Big Bang creation model.
Now, very quickly, a little slight scriptural connection to this. So this is a soft concordance approach now, which I completely affirm, even though I'm fans of Heiser and Walton, but as you also know, I try and encourage them. The concordance model is right on the money in my opinion, because and I tell them, look, the New Testament authors were concording, say, Isaiah's prophecies of Jesus, right? They were concording those texts to Jesus, even though there was an original context. So, as you were just explaining, up until that CMB temperature curve and so on. I want to show in one of your books, A Matter of Days, you highlight Isaiah 40 verse 22, where there's two types of stretching going on. So he's the one who stretches, and literally in the Hebrew, the grammar here, it's like in the past tense. It's like it's a stretched, thing. So he's the one who stretches out the heavens like a curtain. But then the word for spread, and spreads them like a tent to live in, is a continuing action. And that's exactly, again, in Big Bang cosmology, you have the inflationary event, and then now the dark energy taking over. So, yeah, feel free to make a comment if you want.
Sure. In fact, I just finished a book that's now in our editorial on dual revelation, where we look at biblical inerrancy, the two books, the book of Scripture and the book of nature, being books that God truthfully reveals himself to us, and then looking at concordism, not just scientific concordism, but historical concordism and moral concordism, and how we see that in these different books. And, and I respond to people like Heiser and Walton and many others, Enns and Sparks. And, a lot of people think this debate is just about scientific concordism. It's evolved. What's happening about the people that deny scientific concordism, they're now saying we also have to reject historical concordism. The Bible does not have any fulfilled prophecy in it. But the concordance, and you've made the point, this has been going on for the past 19 centuries. It's not just a 21st century issue.
Yeah.
And, if you look at the New Testament, you see these New Testament authors citing the Old Testament saying, Jesus was predicted in the Old Testament, and this is how it was predicted. And so the fact that the Bible explicitly talks about historical concordism, I think gives us grounds to argue for scientific concordism. And one of the chapters I got in my new book is, if we go down the pathway of Enns and Sparks and Walton and Heiser and others, then we're basically conceding the evangelistic turf to the Buddhists, the Hindus, and the Muslims, because they're very aggressive in a concordist approach to promote their faith. And so the book kind of ends, hey, if we theologians are actually going to be able to make some progress in resolving these issues, we need to be evangelists. We need to be committed to bring people who are not followers of Jesus Christ to look at the evidence and to become followers of Jesus Christ. Because if we don't do it, we're going to be marginalized by Islam, by Buddhism, by Hinduism. And in fact, I have an interesting chapter you might like in that I look at Hinduism, Buddhism, and Islam and say, in each case, it's strong concordism. It's not soft, it's not moderate, it's consistently very strong. And to find strong concordism is what you see, especially amongst Hindus and Muslims, where they look at their holy books and say, well, on this page, it mentions the moon. And 3 pages later, it mentions humans. Therefore, that's a prediction that men will walk on the moon. Well,
yeah.
That's how extreme their concordism is. But the point I'm making is what's unique to Christianity is we can make a moderate concordist case where we say we're not looking at vague statements. We see specific statements, and it's not a single statement. I mean, when you look at the Bible, I think, I run into theologians that say, I'm not sure the Bible really speaks about continual ongoing expansion. In fact, what I put side by side in my new book is a theologian, John Ray, who's looked at the Hebrew and says, hey, the verb natah is in all 3 Hebrew verb forms. This clearly is promoting cosmic expansion. But side by side, I put a critique of that interpretation from Vern Poythress. And both of them really like the idea of putting it side by side. But making the point, this is something that doesn't happen in Islam or Hinduism or Buddhism. In Christianity, there's a dynamic debate going on. To what degree can we see and promote moderate concordism in Scripture. But what's interesting amongst theologians, there's absolutely no debate at all that the Bible explicitly and repeatedly teaches the universe has a beginning, and it's a beginning that includes the beginning of space and time itself, and that the universe is governed by laws of physics that don't change. They're constant. And one of those laws is a pervasive law of decay. So those three things are not disputed. There is a debate going on. Hey, does the Bible really talk about ongoing cosmic expansion? But those three features, space-time beginning, constant laws of physics, or one of those laws is a pervasive law of decay, those are three fundamental features of the hot Big Bang creation model. I look at the cosmic expansion part as a bonus. I'm convinced, given the 11 different texts, that the Bible really does speak about this. And in one debate I had with Michael Shermer, the executive director of the Skeptic Society on a university campus, he was saying, Hugh, you're a 21st century astronomer. You're just seeing this in the biblical text because you have this bias. You know Big Bang cosmology is correct. And so you read this into the text. But my response to him was, it's not just me. Christian and Jewish theologians going as far back as 1100 years ago read the same texts and drew the same conclusions. So I wound up writing an article documenting what these ancient Christian and Jewish theologians discerned in looking at the Old Testament. And all four features were discerned by them going back at least 800 years ago.
And again, just to summarize what you're saying there, because I've taken upon myself to if like, I appreciate all the work you've done, but if you're going to appreciate an author's work, so for example your work, check the footnotes, because your books are just stashed full of footnotes and a bibliography to like a rabbit hole. You go check it out. So in Matter Days, you start the first couple of chapters, the wisdom of the ages. So like you go through, say, Second Temple Jewish. So in this case, the Jewish, like say Philo, right? Then you lead into end of the first century, then the patristics, and all the way up to Newton. And I decided to go, you know what? There's no harm in checking it out. Like, check out the Hexameron. Like, let's see what Basil the Great said in the 3rd century. And you see this very interesting sort of the biblical text is correcting the false Greco-Roman cosmology. So, for example, Basil says, well, based on my reading of Rakia, it's foolish. Literally, he says it's childish and foolish to think of the sky as a solid dome. And then he gives a very interesting perspective on, when you look at anything solid, there's always some imperfection. But the sky looks so smooth and clear, it must be something else. Like obviously he didn't know what, but this is the Bible. As time progresses and as the church sort of grew and was ruling out superstition. So here's a religious text encouraging people to think critically, not superstitiously about nature, right? And so therefore, obviously it takes time to de-psychologize people from a superstitious way of thinking, but that's the point. That's why Reformation Europe happened the way it happened, and that's why the scientific method happened the way it happened, because then that was the right time where the majority, which is again mostly Christian, start to they go for it scientifically, and then Copernicus, Galileo, like all the way through. You mentioned Michael Shermer again to to point out an irony in that debate. So Shermer came up with a so-called contradiction in Genesis 1 about the plants existing before day 4, right?
Right.
And you, again, you're sticking to your guns. You're not afraid to but that shows true scientific humility on your part, where you're like, I'm going to stick with the model still, and again, whether it's corrosive or beneficial, one of those things will happen, right? So you told Michael Shermer, I wouldn't be surprised if a month from now, or maybe a couple of months, if there's a paper that comes out saying that plants, or in this case, some form of vegetation, instead of it existing, say, 400, 500 million years ago, may be pushed back to Precambrian.
Right.
And sure enough, actually a month after the debate, that was the amazing thing about it. A month after the debate with Shermer, a paper came out pushing it to, I think, 1.2 or 1.9 billion years, in that range, like
Right.
isotopic evidence. Yeah, briefly summarize that, and then we'll go back to the slides, because that to me is humorous, because he's saying you're reading this into the text, but you're making predictions, and not just predictions about what the text is saying and what you think might happen scientifically, but like if ever there was like the timing of that, it's within 4 weeks of that debate, like verification and vindication on your part took place.
Well, I've debated
So
Michael Shermer 4 times on different university campuses, and it's always on the topic. I mean, does the universe reveal the existence of God? But what I found with Michael, it doesn't matter what the topic of the debate is, he always goes straight to Genesis 1. And so, and he's not really read anything I've written on Genesis 1. It's like, I've been writing on Genesis 1 since 1973. I've yet to get him to read anything I've written on it. I read his stuff. He doesn't read my stuff. It's like, hey,
right.
If you're going to debate somebody, at least read what they've written. So, but he made this bold claim to the university audience. Reasons to believe has this testable predictive creation model. But here's a clear-cut case where one of their predictions has failed. They're claiming that Genesis 1 is factual and chronological, and the text says vegetation shows up before animals, vegetation on the land before animals in the seas. Now, my response in that debate was, well, Michael, animals have shells and skeletons. Therefore, they're going to be well preserved even over hundreds of millions of years. With vegetation, you're going to get decay. So it's going to be very challenging for us to find the evidence. Genesis isn't falsified. You're just simply explaining something that we can't detect yet. But I said, let's give this some time. And I'm making the prediction that Genesis 1 will be vindicated. We will find evidence that vegetation on the continental land masses predates that of the animals in the oceans. Now, I was quite confident about my prediction because I was recognizing in our model, there's no way you're going to get the oxygen that the animals need in the oceans if you don't have a significant abundance of vegetation in the continents. You got the great unconformity, which jumps up the oxygen content. It's not going to provide the oxygen if you don't have lots of vegetation on the continental land masses. But you're right. Within a couple of months, a paper got published in Nature, the world's most prestigious scientific journal, saying we found scientific evidence, isotope evidence that establishes that vegetation has been just as abundant on the continental land masses for 200 million years before the first animals show up in the ocean as the 200 million years after the animals show up. And then 2 years later, another paper got published in Nature where we said we don't just have isotope evidence, we've actually found the fossils of vegetation on the continental land masses. Now, they qualified that. They said we don't have complete fossils, we've only got fossil parts. Again, vegetation decays quite easily. The biggest fossil part they had was 1 millimeter across. So tiny fossils, explaining why they hadn't been discovered earlier, because all that remained were these fossil parts. But it demonstrated that vegetation was abundant on the continental land masses for 600 million years before the first appearance of animals in the oceans. So
and
again,
that's the 1.2 billion mark over there.
that's the 1.2 billion mark.
Yeah.
Vegetation dates back at least that early. I think it'll date back earlier, but there again, we have a problem of trying to discover something that's going to be extremely challenging to discover, given how easily vegetation matter decays.
All right, let's finish off with the Big Bang summary, the model that scientists use. So that's the cooling curve. Now, you did something very interesting with this. I like this mechanical efficiency analogy you're using here. In other words, based on everything you've explained so far, leading up now to the curve and so on, um, this analogy is quite interesting because you're tackling this in light of the other models that's proposed, like cyclic universe and so on.
Right.
And this in itself actually totally says no, it only has to be this particular model because again, look at the efficiency of with respect to our universe. So
Yeah, here we're
yeah.
talking about entropy. And,
Mhm.
when you drive an automobile, you can't have an automobile that converts the chemical energy in the gasoline into 100% kinetic energy. Because of thermodynamics and entropy, you're not going to get 100% efficiency. But the amazing thing is, we do have automobiles and trucks that have a very high level of efficiency, very close to the theoretical limits that you would get from our understanding of gravity, electromagnetism, and thermodynamics. A diesel engine in a truck is really close to the theoretical maximum mechanical efficiency you can get from burning some kind of fuel. 40%. Gasoline engine, 30%. I happen to drive a car. It's not a hybrid, but I get very close to 40%. So we're getting improvements since then. Steam engine, which is what you have, say, with trains 100 years ago, 13%. When you consume a hamburger or a hot dog and try to transform that into human kinetic energy, it's only 1%. That's at best. Often it's more like a 0.1%, but you can get it as high as 1% if you're in really good physical condition. But the universe is the highest entropy system we measure. And you can see there that the specific entropy measure of the universe is about 100 million. So that's why you get that extremely tiny percentage. But I wrote this basically making the point that Hinduism, which is fundamentally based on reincarnation, that everything goes through these cycles, and it's fundamentally based, they talk about how all life reincarnates. Well, it's fundamentally based on the Hindu belief that everything reincarnates. And you see this in the Vedas, that the universe reincarnates, that every 4.32 billion years, we go through a death and a rebirth of the universe. But for that to be scientifically plausible, it's necessary that there be enough mechanical efficiency in the universe that you could get a restart. And what you're going to need is something in the neighborhood minimum of about 1%. And what we're seeing here is that the Hindus are off by a factor of 100 million times. The universe is 100 million times way too entropic to support their idea. And you mentioned the oscillating universe model, very popular in the 1980s, but it's basically a Hindu concept. And they were saying, why do we need just one beginning? Why not repeated beginnings? And incidentally, the oscillating universe model is coming back, but I think it's coming back because lay people really don't understand the motivations of mathematical astrophysicists. And so there are journals out there like Physics Letter B, where they allow the authors, the mathematical astrophysicists, to speculate and say, well, we know this isn't the real universe, but what if? And they come up with all this mathematics. So you got people like Roger Penrose who's saying, let's actually pretend that the universe can have a previous contraction phase that can lead to an expansion phase so that we don't really have only 14 billion years. We can expand things. So he's basically reinventing the oscillating universe model. But if you actually read the debate he had, the written debate he had with Stephen Hawking, he was asked this question: hey, you've developed this mathematics. Do you think it's credible? And he basically said, the mathematics works, but it's physically impossible. That you can't join the geometry of a collapsing universe to the geometry of an expanding universe. It's the same argument that Roger Penrose said, yeah, we can mathematically conceive of wormholes where you connect the singularities of two black holes so that you can go from one space-time realm to another. Mathematically, we can make it work, but we know it's physically impossible. The probability of the singularities of two black holes perfectly touching one another is zero. The probability they remain stable, likewise, is zero. But the math works. And so we're at a point, back in the 1980s, when they came up with this entropy measure, they said all oscillating universe models are off the table. They're ruled out. And theologically, Hinduism is ruled out. And also all the Buddhist sects that have copied that Hindu concept, they're all ruled out. But as Roger Penrose points out, we can still make the math work. But physically, we know it's impossible.
Right. Because and in that sense, math is just a tool. I mean, math can't lie in the sense if you're working within the parameters of math, say grammar, the grammar of math, but
yeah,
it's still a tool. It's not. It's depending on what reality says.
He said, look at my assumptions. I'm not claiming my assumptions are realistic. I'm saying with these assumptions, we can make the math do X. And and mathematicians do that all the time. I mean, I had a math professor when I was a student who was working on a problem of trying to take spherical oranges and put them in a cubical box where there's no spaces between the oranges. So utterly impossible in 3 dimensions of space. But he wrote a paper where he said, we can make it work in 1 million independent dimensions of space. Now, does that mean that you can market cubical boxes that'll hold oranges with no spaces between them? No. It was mathematical speculation.
Okay, now this is the Abel 370 Galaxy Cluster. Now is James Webb. Now this is in your 4th edition. And to be honest, in your 4th edition, when I saw this, I'm thinking this looks as clear as one of the James Webb photographs. But yeah, like I'm also noticing maybe some gravitational lensing as well taking place. Yeah, you do see some
gravitational lensing, right?
Yeah. Now, is James Webb going to look in this direction? Like, what's the implications of this photo?
What I've showed people on my Facebook page is a Hubble Space Telescope image of the galaxy cluster SMACS 0737, and the very first Hubble Space Telescope image of the exact same cluster of galaxies. And what you see in the Hubble image is maybe 3-4 instances where you can see gravitational lensing. In the James Webb Space Telescope, where the image was taken in just a tiny fraction of the time that it took for Hubble to get the image, you can see dozens of gravitationally lensed more distant galaxies. Moreover, unlike what you see with Hubble, you can look in the background and see beyond the cluster of galaxies hundreds and hundreds of much more distant galaxies, beautifully imaged, where we can actually identify what kind of galaxies they are. And this image of Hubble, yes, you do see more distant galaxies that are not members of the cluster, but they show up as tiny dots. And the James Webb Space Telescope, you can see which ones are spiral galaxies, how big they are, which ones are ellipsoidal, how one galaxy is interacting with another. So we're seeing incredible detail. And because of the size of the James Webb Space Telescope and the fact that it's an infrared telescope, because you look at the distant universe, everything's redshifted. So the light is much brighter in the red infrared part of the spectrum than it is in the visible spectrum. So we're literally able to get per unit time about 100 times as much astrophysical information with James Webb as we can with the Hubble Space Telescope when we're looking many billions of light years away. But if people want to see them, I've got several images on my Facebook page. I'll put it on my Twitter page as well, where you can see the very best that Hubble's been able to demonstrate side by side with what you get with James Webb in just a fraction of the observing time. And it's just a mind blower how much more we're gaining from James Webb. And same thing with that background shot you've got of the Carina Nebula. I showed that side by side with the best that was achieved by Hubble. And when you look at Hubble, you can tell that there's a nebula there, but you can't see any of these detailed elephant trunks where stars are forming. Whereas you look at Carina, you can literally see in just one James Webb Space Telescope over 50 of these dark gas clouds that are in the process of collapsing to make stars. Whereas with Hubble, maybe you could see one, but not with any great detail. A lot to look forward to.
And this one you say is the most. This is NGC 4945, the galaxy that's most similar to the Milky Way. Oh, sorry. I should. There we go. I accidentally put both of us at the side. Yeah, is James Webb going to look at this particular galaxy for any more details?
Well, top priority for James Webb is to look at the most distant stars, hopefully with a goal of finding stars that are made of the initial components of the Big Bang universe, which would be about 74% helium, 75% helium, 75% hydrogen, 25% helium, and just a trace amount of lithium. No telescope has the power to see stars that are made of the initial elements of the Big Bang universe. James Webb has a shot at it. It's not a guarantee. It will only work if the very first stars are really big, hundreds of times the mass of our star, the sun. And if you get a cluster of those stars, James Webb will be able to detect it. And the bigger the star, the faster it burns up. And stars that are coming in 100 to 200 times the mass of our star, the sun, they literally will burn up in a few 100,000 years, maybe even just tens of thousands of years, which means those stars will not have time to be polluted by the ashes of previously burnt out stars. And so that's one of the big goals of James Webb. Can we actually look far enough away, far enough back in time, that we can see the firstborn stars, the really big ones, that have not been polluted during their formation stage? Another big objective is to actually examine how do galaxies form, and that requires looking at star clusters that are merging together 13.5, 13.6 billion light years away. So that's at the top of the agenda of projects for James Webb. But another big
factor, that's going back that's going back 200 million years shy of 13.8 billion years, which is the age of the universe.
Well, the most distant galaxy observed by Hubble was 400 million years after the cosmic creation event. And literally just a week ago, James Webb was used to produce the 6th image, because NASA released 5 images for publicity to get the public excited about how wonderful this telescope is. But image number 6 was the first really serious observational effort, and was designed to try to detect a galaxy that's even more distant than the farthest galaxy detected by Hubble. And it's at least 100 million years earlier, and maybe as much as 250 million years earlier. Follow-up studies will give us a better measure of its distance. But it's actually affirming Big Bang cosmology, and that this galaxy weighs in at just 1 billion times the mass of our star, the sun. And that should be the high end of these small clusters of stars and gas that are beginning to merge together to make bigger galaxies. But project number 3, that's also very high on the priority list, is to measure the chemistry of nearby exoplanets. Because, we've discovered over 5,000 planets beyond our solar system, and there's only a handful where they've been able to make an estimate of what the atmosphere is composed of and whether or not there's water on that planet. In fact, only 2 Earth-like planets have they been able to measure the water content, and in both cases, it came in at 500 times as much water as what we see here on the Earth. And that's something that's actually alerted astronomers. If you want life, the planet cannot be bone dry. You need water, but you don't want a lot of water.
Exactly.
And 2 other planets that we found outside the solar system where we've been able to measure the water content, it's been way too high. Their ocean depths will be thousands of kilometers. And with ocean depths that deep, you not only have the possibility of water floating on the top, because of the density of water, you're guaranteed to get frozen water on the bottom. And that means you're going to have the rock of the planet permanently isolated from the liquid water, which eliminates the possibility of life.
Right.
But with
Now,
James Webb, we're going to be able to prove all that.
Now, near the end, so I think this is what you're getting at just a moment ago. The relative abundance of advanced life-critical heavy elements in Earth's crust. I think you were comparing with, magnesium?
Magnesium and iron.
Yeah.
And because manganese. It's manganese and iron, where you kind of see amongst all the rocky planets and in our Milky Way galaxy and in the universe. Those are relatively constant. We would expect them to be because of the way stars fuse hydrogen. It's quite predictable how much iron and manganese you'll get. And so I compare the abundance of the elements in Earth's crust with what we see everywhere else in the universe where we take away the hydrogen and the helium. Because the Earth is a rocky body, but it has a relatively small mass and a relatively, a large escape velocity, which means we're not going to retain any hydrogen and helium in the atmosphere. And hydrogen and helium make up 98% of the elements in the universe. So what I've done is I've said, forget about the hydrogen and helium, because we want to see how Earth looks compared to what we would expect with other rocky bodies in the universe. And so taking out the hydrogen and the helium, which you see here, with the exception of just 2 elements in the periodic table, everything on planet Earth is anomalous. We either have way more than the rest of the Milky Way galaxy or way less. And it's the same number with the universe, either way more or way less. And in each case, the anomalous abundance that we see on planet Earth is exactly what you need to get advanced life. So if you look at sulfur, for example, Earth has 60 times less sulfur than what you'd expect in other rocky bodies. And in this case, it's not, in some cases, Mercury and Venus and Mars have not quite the same anomaly as the Earth, but some of it. But in the case of sulfur, only Earth has 60 times less. If you go to Mars, it's got 60 times more sulfur. So I remember watching The Martian with my 2 sons and kept telling them, Matt Damon's not going to be able to grow potatoes on Martian soil. With 60 times more sulfur, he's not going to be able to grow anything at all. He's going to have to import the Earth soil. And it's everything else you see in this table.
Right.
Look how much more potassium the Earth has, 90 times more. And, potassium is essential for plant and animal life. And ours is
And
the only planet.
mm,
We've got the just right abundance.
and uranium and thorium is for the volcanism in the Earth's core, like radioactivity to
Right.
cause, yeah. Uh, and
Well,
and
you'll
here's
notice in this chart you're
hmm
showing here, I got asterisks by some of them. The ones where
hmm
you have asterisks, I refer to those as vital poisons. If you've
mm,
got too much in your body, it will kill you. If you've got too little in your body, it will also kill you. They have to be fine-tuned. So you need
mm,
sulfur in your diet, but it has to be at just the right level. And by the way, you also need arsenic in your diet. If you don't have any arsenic, you will die. But I can tell you, you only need a really tiny amount. Too
mm,
much will kill you. So it
mm,
has to be at just the right level. But the ones without the asterisk are those that are crucial for maintaining our civilization and maintaining the habitability of our planet. So the two that are the most anomalous of all, well, the three are lead, uranium, and thorium. And lead exclusively comes from the decay of uranium, thorium, neptunium, and plutonium. That's where all the lead comes from. So we shouldn't be surprised that lead is so super abundant in the earth. It's because uranium and thorium are super abundant. And
and
we're here.
it's taken 4.5 billion years to decay to lead, hence proving a 4.5 billion-year-old Earth. And yeah,
It does, yes.
yeah,
But
mm,
because Earth is so incredibly endowed with uranium and thorium, there's enough heat in the interior of the Earth that even after 4.5 billion years of the formation of the Earth, the core of the Earth is hot enough to have a liquid iron core where we have a solid core that allows for the diffusion of light elements in that solid core to diffuse through the liquid core and circulate it so that we get a dynamo. And with a dynamo, you get a magnetic field, and it's that magnetosphere that prevents the radiation of the sun from sputtering away all of our atmosphere and from sputtering away all of our liquid water. That's that magnetosphere that has enabled a long history of life on planet Earth and has made possible our existence as human beings at the optimal time in the history of the sun. None of that would have been possible if our Creator hadn't super endowed our planet with an enormous amount of uranium and thorium, literally 600 times more thorium than we would expect any other rocky body in the universe. And
mm,
likewise with uranium. And one of the books I wrote was Weathering Climate Change.
hmm
And one of the points that I make is if we want to really resolve our global warming problems that we're facing and restore climate stability, thorium is a wonderful way to do it because we can build thorium nuclear reactors and we can get energy so cheap from thorium nuclear reactors, we would get electricity for about half the price of water power, which
mm,
currently ranks as the cheapest energy source on the planet. And none of that would be possible if we didn't have all this thorium. And by the way, we've had thorium nuclear reactors dating back to 1960, and no one has bothered to scale it up because back in the 1960s, they said, we don't need these thorium reactors. We don't want them. We can't make nuclear weapons. But what I think is exciting today, that's actually an advantage. We can give thorium nuclear reactors to countries like North Korea and have no fear they're ever going to use that to make nuclear weapons. If you
mm,
try,
mm.
you'll die. So it's not impossible to make a nuclear weapon from thorium, but if you try it, it's going to kill everybody that's involved in the project. So it's never
Mm,
going to happen. And unlike uranium, the ore is safe to mine, and the toxicity, we're talking just 50 to 100 years with which you have to store the nuclear waste before it's safe to handle. With uranium, you're looking at 50,000 years.
right.
So I look at this as one of the blessings of our Creator. He
hmm
gave us a huge amount of thorium. And by the way, Australia
mm.
got one of the richest reserves of thorium in the world.
That's right. And you make mention of that in weathering climate change as well. And Now, folks, now notice. So this is near the end of Hugh's summarization of the big picture of, say, the Big Bang, the universe, right? So notice, as Carl Sagan would say, this is stardust. What we're seeing here in this table. Fancy. It's a poetic way of saying, supernovas and at the core of stars, it starts with hydrogen and then it fuses it all together, and then you get these heavier elements in the periodic table. Now, notice you have the arrow of time in one direction. You have the universe starting from practically this tiny, infinitely near infinite small, but very high energy point, expanding out at this very careful, you know, expansion, dark energy. Like I remember Krauss even saying, 10 to the 122nd power or something, a very
Right.
fine-tuned
Highly
parameter,
fine-tuned. Right.
right? To then bring about all the stars that's come and gone, to then produce the elements, right? To then produce, in this case, now the next slide would be, say, our Milky Way. There's the sun. There's the location of our sun and where our Earth is. So all that you're seeing there in this Milky Way is stardust. And so coming back to this list here, that means Earth then, for advanced life as it is to exist, at this moment in time, so, well, starting from 4.5 billion years ago up until now, in that range, we are practically, as you predict in Origin of Life, in your Origin of Life book, with respect to the other book that you wrote, which technically is not really well known, but I wish it was, Lights in the Sky and Little Green Men, where you say, even with respect to the ET question, we are practically the first advanced brains to possibly come about in this universe. So the point is, everything that's transpired in a so-called, let's presume, an atheistic universe, right, has led to this planet to be endowed with exactly this form of ratio of elements. Do you see how ridiculously improbable that is? And Francesco Ayala, made a very crude mathematical measurement that, from single cell to humans, it's like 10 to the minus 1 million probability that can happen. But then
Right.
Frank Tipler and another astronomer, I forget his name, but he took Ayala's calculation, and they were like, but if you include everything we've just discussed, it's like 10 to the minus 27 million
Right. Right.
probability. So this, yeah, notice from the 80s till now, this is the discovery that we've this is now
Well,
the,
this table you
yeah.
see here is in my book Improbable Planet, which was released
Hmm.
in 2016. And yeah, I included it because in each case, it's remotely impossible from a naturalistic perspective to get that anomalous of abundance of that one element on one rocky planet. But it's not just one anomalous element. Virtually the entire periodic table has these exquisite anomalies that are all just right, all essential and crucial to make possible the existence of human beings on that planet. Now, what's in my brand new book, Designed to the Core, is discoveries that have been made in the past year and a half that actually explain how it was that Earth and Earth alone got all these unique abundances. And so, discoveries about what kind of neutron star merging events, where they have to be, where the solar system has to be born. It can't be born in its present location. This is all new stuff. So now we don't just have the raw data, we got explanations of all the miraculous fine tuning that needs to come into play for this to be possible.
Absolutely fantastic. That it just it yeah, that's just amazing. I can't wait to read the book. Um, all right. I think we have like 10-15 minutes left. I want to respect your time, Hugh. So now let's quickly summarize your blog posts in relation to James Webb. So, in 2008, title of your blog post, White Dwarfs Deliver Better Creation History. And if I keyword search the James Webb,
Right.
you write here saying the team concludes their research study by pointing out that until the launch of James Webb, their new method will be limited to nearby globular clusters. This is because the coolest white dwarfs are extremely faint, and given current technology, their method will be confined to a reanalysis of Messier 4 and all of these and so on. So
Right.
what was
Yeah,
your
the
hope
point I'm
back in
making here
2008?
is
Yeah.
that, I've been doing astronomy since I was in my childhood years, and that was a time where they were using nuclear burning stars to try to measure the ages of open clusters and globular clusters. And this article that I wrote a few years ago is making the point we can get much more accurate and highly reliable age measurements of globular clusters and open clusters if we use a different method. Don't look at the nuclear burning stars, what's called the Hertzsprung-Russell diagram and the turnoff point, but look at the cooling curves of burnt out stars. And so when a star goes through its nuclear fuel, where the star is only slightly bigger than the sun or smaller, it ends up as a white dwarf. That will be the future of our star, the sun. It will become a white dwarf. It runs out of nuclear fuel, but when it runs out, it's still quite hot, about 30 degrees, 30,000 centigrade. It begins to cool, but it takes a long time to cool down. One reason why we know that the universe isn't very old, there are no black dwarf stars. We see no stars that have been completely cooled down, but we see lots of stars. About 20% of all the stars we see in our galaxy are white dwarf stars. But what this paper is pointing out is that a typical globular cluster is going to have hundreds of these white dwarf stars, and depending on the mass, they'll be cooling at different rates, and it provides us with a really accurate measurement of the age of that cluster. However, because these are burnt out stars, the stars are quite faint. And so with current telescopes that existed when I wrote this article, we could only look at 3 really nearby globular clusters to make these measurements. And it's like, if we really want to fine tune the biblically predicted Big Bang creation model, we're going to need to be able to look at all 150 globular clusters in our Milky Way galaxy. And it'd be really great to look at some of the globular clusters in the Andromeda galaxy and in the Large Magellanic Cloud. And that's where people said the only way we can do that if we get the James Webb Space Telescope funded. And that was a big factor in persuading Europe and Canada and the United States to fund the telescope, saying this is going to give us way more precise age measurements of clusters throughout our Milky Way galaxy. And there's no other way we're going to be able to get this. So that's another big aim of the James Webb Space Telescope, is to take us beyond just the 3 nearest globular clusters.
Now, the next one, I think you've already mentioned this like a couple of minutes ago, Hugh. Finding oceans. So this is the following year, 2009,
Right.
finding
Right.
oceans and continents and extrasolar planets. Keyword search James Webb. Now, originally it was predicted to launch or scheduled for launch in 2014, but
Right.
there's a lot of pushbacks. But
Yeah.
again, what was your hope in relation to this blog post?
One of the reasons why the James Webb was delayed, there are several reasons, because they kept coming up with new technology that they said, we got to put this on the James Webb. And so people say, hey, a cost overrun has started off at 1.5 billion. It ended up at 10 billion. Well, it's not just government waste. What happened was astronomers were saying, hey, we built this New Worlds Observatory, and we were testing, but using an occulting factor in the telescope to block out the light of the star so we could see the faint light of planets orbiting that star. And with ground-based telescopes, this could only be done on the very nearest planetary systems, and not with a whole lot of really high accuracy data, but it proved that the principle works. And so they said, we need to redesign the James Webb Space Telescope so it has this occultation technology. Because once we get it beyond the atmosphere of the Earth, this is going to be way better than anything we're able to pull off with the New Worlds Observatory. We're going to be able to perfectly cut out the light of the star, and with the James Webb's huge mirror, we're going to easily be able to see those planets. And not just those planets, we're going to be able to use the spectrographs on the James Webb to measure the chemistry of the atmospheres and the oceans of that planet. But the New Worlds Observatory said, with this occulting feature, we can determine whether or not the planets have surface oceans and surface continents, or whether it's just a water world where there's only water on the surface, or whether it's a world where there's only land mass and no water at all. And with the New Worlds Observatory, they said, well, we think we found a planet that has somewhere between 5% ocean coverage and 95% ocean coverage. So the error bars were huge. But they said for James Webb, we're going to be able to determine rather precisely, at least for several hundred planets, what that ratio of continents to oceans is. And even if there exists, I mean, that's one requirement for advanced life, or even for long-lasting life. Even if you want bacteria to exist for, say, 1 billion years, which is essential to chemically transform the planet for more advanced life, you're going to need coexisting continents and coexisting oceans, where it's not 5% to 95%, but more like what you see on Earth, 10, 20 to 30% continental landmass coverage. And astronomers are predicting we're not going to find any. Earth alone is going to have that capability, but James Webb can actually put that to the test.
And by the way, for Earth's, I mean, the very fact that even Earth even has what it has, it's like, as you point out in your books, when you look up in the night sky and you see the moon, the whole moon formation event, like a planet may need to have its own moon formation event.
Well, that's quite possibly that's in my book, Designed to the Core.
Oh, okay.
A brand new habitability discovery. If you want life of any kind, not just advanced life, but even microbial life, it can only happen on a planet-moon system where you've got a planet that's identical to the Earth in its features, orbited by a moon that's identical to the moon, where they have identical to the Earth-moon system, the origin, where two rocky planets are colliding with one another, where the collision gives birth to a moon that orbits the Earth closely, where the moon begins to spiral away from the Earth. All that's necessary to prevent the planet from having its atmosphere and its ocean sputtered away by the intense particle radiation of the early star. Because what you'll see in some of my books is that you go back to the first 500 million years of the solar system, the sun's particle radiation and X-ray and gamma ray radiation is more than 10,000 times intense as it is today. So intense that unless you've got a coupled magnetosphere, where the moon has a magnetosphere, the Earth has a magnetosphere, and they're close enough together that they couple, all that's necessary to prevent the radiation of the early sun from making our planet bone dry with no atmosphere. And so if we're going to find life beyond our solar system, it can only exist on a planet-moon system identical to the Earth-moon system with the identical origin and the identical history. And the paper that got published, they just said, this is a new habitability requirement. But what I wrote and put in the book Designed to the Core Yes, it's the most recent habitability requirement discovered, but it's also by far the most stringent. The probability of that happening without supernatural intervention is mind-bogglingly remote.
Right. Um, Now I have one, two, three, four, five, six. I have 7 of the blogs up, but I don't know if we have time to go through each one.
Well, I
But
think that's going to have to be another episode
yeah,
that we do
yeah,
together,
yeah, yeah,
because I actually made copies of all the ones that you suggested me do. And when
yeah.
I did them
Right.
all, I said, this is a whole episode just to go through
Yeah.
all of these. But I think it
So,
makes a wonderful
mm,
point that you made earlier. We at Reasons to Believe have been writing about the potential of the James Webb Space Telescope to put our biblical creation model to a far more stringent test than what's been possible with existing telescopes. And
yep.
so these articles are loaded with predictions of what James Webb will be discovering. And
Hmm.
hey, in the next year or 2 or 3, we'll see how it goes. But I'm confident that the Bible is going to pass with flying
Hmm.
colors.
What I'll do is, for the sake of time, I'll quickly read out the title of each
Sure,
of
that'd be
the
great.
blog posts for the audience. So the next one up was in 2012, Fossils of Primordial Galaxies Shed Light on Creation. Then the next one after that, and by the way, these are um, with respect to the mention of the James Webb, like when you mention James Webb in these blog articles. So then 2015, Finding the Firstborn Stars, and I think even in your paradox class in 2015, you started talking about this.
Right.
Um, then let's see. The quest to discover the nature of 70% of the universe.
Yeah,
This
dark
is
energy.
right, and that's in now notice the jump, right? So 2008, this is now 10 years later, 2018. Um, then helium helium
Helium
hydride
hydride.
detection affirms Big Bang creation model, 2019. Now, this one, just quickly, this is an interesting one. Like James Webb, I think this is connected to what you're getting at a moment ago with like spectral analysis of, when you look back, far distances and so on. Okay, then the next one after that, okay, this is why I remember you mentioning this in the paradoxes because you bring, so in 2015 you wrote about the firstborn stars, and then in 2019 you bring that to the forefront. You're like, oh, remember when I spoke about it? So like, yeah, pursuing the firstborn stars in a better cosmic creation model. And then the last two is, this is an interesting title, again in 2019. Are astronomers confused about the cosmic creation event? Is that a is there a reason why you? I mean, if you want to spoil
Well,
it, like,
yeah, the spoiler is that Young Earth Creations is saying Big Bang cosmology, it's gone because look at these discordant measurements. And
hmm,
I went to graduate school with Barry Mador, and he was the one that jumped in and said, well, we see this discordance because we've been using Cepheid variable stars. If we use tip of the red giant branch stars, which have different systematics, let's see if this confusion goes away. And indeed it did.
hmm,
It went away. So, and that's the wonderful thing about astronomy. We don't just look at the statistical errors, we also look at the systematic errors. The
hmm,
different physics is going on, these different bodies. And when you get consistency, then you know you've taken care of the systematic errors.
hmm. And yeah, yep. The point that you're making here is once this is up and running, it's like it goes below 1%, and
Yeah, James
it's
Webb
like,
has way more accurate data. So,
right.
and so we're predicting that this tension between the expansion of the universe based on nearby stars, contrasted with the value we get from the measurements of the cosmic microwave background radiation, we're actually looking at the cosmic expansion rate when the universe is only 300,000 years old. We're predicting that James Webb is going to resolve that because it's actually powerful enough to actually use a telescope to look at the cosmic expansion rate really close to what you get from Planck and just see what we get.
And then the last blog post was published earlier this year, April, taking the Big Bang's temperature. And near the end, you speak about what's next, and sure enough, the James Webb will be used to, right.
It's taken us 40 years to make 13 measurements of the past temperature of the cosmic background radiation. James Webb is going to be able to add about 30 or 40 more. So we're going to go from 13 to nearly 50 thanks to James Webb.
Yeah, that's like every 3 years. I mean, 13 measurements in 40 years, right? That's like every 3 to 4 years, only one measurement. Yeah. Now, just before we close, there is one super chat question directed to Hugh. Does Dr. Hugh Ross have any updates, if any, plan to excavate the moon surface has been proposed to look for ancient fossils? You know, the whole moon fossil thing and origin of life.
Well, I hear that the Chinese are very interested in pursuing this issue. And I know a few Chinese research scientists, and they say, the problem with you Americans, you're intimidated by Charles Darwin. We're intimidated by our government, but we're not intimidated by Charles Darwin. So we're okay with actually going to the moon and recovering the dust of, Earth transported dust and see what's going on there. Now, recently NASA's announced that they're going to go back to the moon as well. And but what's different from the Chinese, they're actually talking about using sophisticated machines. In fact, I posted a tweet on my Twitter page saying that with technology at the place where it is today, there really is no need to send a human into outer space. We can get way more science for a whole lot less money without risk of doing any damage to the human by sending machines. It's one thing back in the Apollo arena to say we have to send men to the moon because we didn't have the technology to do what people can do. But today, we've got the rockets, we got the machines, we got the computers to gather way more scientific information. For example, there's a mission back from the asteroid Bennu where they sent a machine out there. They grabbed some material from that asteroid, and now that mission is on its way back to Earth, where we're going to be able to analyze that material right in the lab. But NASA's talking about not even bringing it back to Earth, doing all the analysis right there in the moon. And that would save a lot of money. So we'll see.
Well, that's it, folks. Yeah. Thanks, Hugh.
You're welcome. It's been fun.
Susan Slam says hello. She just wanted to say. And I'll see everyone next time. And God bless you, Hugh. Thank you for joining.
You're very welcome. It's been a pleasure.